This work is kind of a spin-off of some work that's described here in these two papers, one published and one in progress. When I was working on this, I thought of voids as kind of a unimportant, trivial topic, and as I got more into it, and it's the usual thing, if you develop a tool that works on something, it suddenly becomes much more important and interesting to you. So basically, this has been an analysis of the Sloan Digital Sky Survey Redshift data set of 160-some, or actually more galaxies, but we selected a volume-limited sample from the Sloan Redshift survey and worked on that. And this is sort of a description of the two kinds of tessellation schemes that can be applied to point data. These, of course, are in 2 dimensions, but you can imagine the same thing in 3 dimensions. And I won't go into the details. On the left is a Voronoi tessellation of some simulated random points. On the right is the dual Delaunay triangulation of the same data points. And I suddenly realized that the Delaunay triangulation was a much better scheme for representing voids in the point distribution. The points are randomly distributed, but avoiding a circle centered at the center of the diagram. And what are colored in different density levels are the cells segmented according to size. You have to try to recover the structure by selecting cells according to how big they are. And the best you can do, the best single threshold for deciding what to call the cells representing the void, shown on the left for the Voronoi tessellation. On the right is the Delaunay triangulation. And you can see the one on the right is much better in several ways. One is the elements that you're constructing the void with are empty, which is what you want. You're trying to represent a void, whereas by definition, any Voronoi cell has one point in it, so it carries with it a non-zero density. Also, you see a better fit to the structure, and you don't have to worry as much about end effects and so on. So basically, this triangulation in 3D is a good way of dealing with voids and representing them. So here's the basic scheme. You start with the 3-dimensional point set, which is, in this case, just a small sample of the Sloan Redshift data with various cutoffs to yield a volume-limited sample. You carry out in 3 dimensions the Delaunay tessellation or triangulation, yielding a set of tetrahedra which partition the whole data space. That is, this is one of the tetrahedra, but if you piece them all together, you cover the whole data space. And the galaxies lie at the vertices of the tetrahedra. Well, if you think about it, you have to decide if you're trying to collect together these tetrahedra into voids, and that's the whole game. These are viewed as building blocks of the void structures, and you want to collect them together. You have to select which ones you're going to use. Here's a histogram of the sizes of the tetrahedra. If you include all of the tetrahedra, it turns out you get a useless representation. You get a single void that represents the entire data set, but it's useless because it's highly convoluted. So basically, you have to decide what sample to use at, in this case, at the high end of the distribution of void sizes. And then you simply collect together adjacent tetrahedron according to some criteria for adjacency, and there are 3 possible ones for in a 3-dimensional array. The one that turns out to be the best one to use is that the tetrahedra are considered adjacent if they share a face. Less restrictive choices end up not being as useful. So that's the basic scheme. It's incredibly simple. There's only one sort of thing you have to fiddle with, is this threshold for the tetrahedra you're going to include in the tessellation. Everything else is completely straightforward, no parameters, no smoothing. And The first thought was that, well, if you look at the distribution of the sizes, volumes or radii, effective radii are defined here in terms of the volume, that looking at the distribution would give you a way of deciding where to cut off the distribution and look at the high end of that. And what's shown here are 3 different histograms of the tetrahedra sizes from the Sloan data itself, from the Millennium simulation, with a data selection meant to mimic our volume-limited sample from the Sloan data, and then a set of random points with no structure at all. And you see that the Sloan data and the Millennium simulation have a very, very similar distribution, very different. The random, as you expect, is narrower, and so you're sort of focused on looking at the tail of the actual data as being the significant non-noisy set of tetrahedra. Well, I actually won't go into a lot of detail, but it turns out even though the edge effects are less important for the Delaunay approach than they are for Voronoi, you still have to worry a bit about edge effects. For example, here's the distribution for the random points in a 2D plot. On the x-axis is the size of the tetrahedra. On the y-axis is the distance from the edge of the data space. And this little projection is distorted edge cells that are bigger than they should be because they're near the edge of the data set. So anyway, you can go through a lot of machinations to figure out what a good cut in both size and nearness to the edge to get your final sample. And here's just a visualization of a sample of a void. This is from the actual Sloan data. This is one void composed of 5 tetrahedra that are sharing faces. And of course, by definition, this void is empty. There are no galaxies in the volume-limited sample within this void. And I should say there are 5 tetrahedra, so I show 5 different plots where one of the tetrahedra is emphasized by shading, and then finally where they're all emphasized, but the shared faces are even darker. Empty of galaxies in the volume-limited sample, but there are fainter galaxies that were rejected from the volume-limited sample. Are any of those inside of here? Well, there are 3. There are 3 faint galaxies that are in this void. It turns out that all 3 of them are very near the edge, very near the surface of this void, so in effect they're really not there. And I'll talk more about these faint galaxies later. Here's just another slightly more complicated example where there are 7 tetrahedra, but the same thing. And I'll just go through some statistical summaries of this analysis, comparing in every case on the darker bar in the histogram represents the Sloan data, and the lighter one is the Millennium simulation data. This is just a histogram of the number of tetrahedra in the voids, and so you see there's a distribution. Many of the voids are fairly simple, only a few tetrahedra, and just a few are complicated with many tetrahedra. Shapes, here's a display trying to get at the shape distribution. What I've calculated is, it's not really complicated, just fit an ellipsoid to the galaxies that sort of circumscribe the void and calculate the moments of inertia of that ellipsoid, and then represent the shape as the ratio of the second largest principal axis is a better term to the largest principal axis, and the second largest principal axis to the largest one. So that a sphere would be up in this part of the diagram. A one-dimensional tube would be over here, and I had to invent some terms for what to call these things. A sheet in the galaxy distribution, this would be called a sheet, this would be called a filament, and this would be called a spherical cluster or a blob or something. So you see that there's a distribution of shapes with a concentration in both the actual universe and the Millennium simulation, sort of clustering around spheres not quite spherical, but somewhat spherical. Another property of the shapes is convexity, which is easy to define. This quantity represents the degree of convexity, a simple volume ratio, the ratio of the volume of the convex hull of the void to the total volume of the void, being the sum of the volumes of the tetrahedra that make it up. A purely convex structure has a unity, and you see most of the structures are pretty convex, but there's, again, a distribution of shapes that have indentations or concavities in them. And then here is, now these are, everything I've shown you before has to do with the, sorry, not quite. This is for the voids. That's for the voids. This is for the, well, sorry. What I meant to say is this is now the distribution of the sizes of the voids. Not, I showed earlier a distribution of tetrahedra effective radii. This is the void sizes, and basically comparing the Sloan data with the Millennium simulation. This vertical line is a cutoff arrived at with after a lot of fooling around with information criteria and cross-validation and various things to decide on what are true voids and what are statistical noise. And another thing you can do, independent of the construction of voids, you can calculate autocorrelation and cross-correlation functions directly from the cells without doing any binning in the spatial coordinate. If you think about it, all you do is do it's kind of an Edelson and Krolik type of correlation function, where the quantity you're averaging is in the case of the Voronoi cell, it's 1 over the volume of the cell, because the smaller cell means higher density. And in the case of the Delaunay tetrahedra, it's proportional to the volume. There's no quantity representing absence of a galaxy. There's no analog I can think of kind of the density, because it's not a density of anything, but sort of a surrogate for an ill-defined quantity is the size of the Delaunay cell. A big cell means a large void or an empty region. And again, you can also do a cross-correlation in the same way, point by point. The only tricky thing is subtracting the mean out is a hard thing to do. And so you see this cross-correlation doesn't go to 0 at large values, and neither do the autocorrelation. So there's some thinking, some more thinking that needs to be done in terms of making this look more like a conventional correlation function that asymptotically goes to 0 or no correlation. And then finally, here's a display of the three-dimensional display of the final catalog of voids with a cutoff based on, like I said, a lot of details. What is shown are the 20 largest voids are shown as full polygons, or polyhedra, I guess I should call these. And then the rest of them, there's several hundred in the catalog. The smaller ones are shown only as these square symbols. And this symbol up here is something that Phil Marshall will explain in the discussion section. Okay, so this is getting back to the question, how empty are these voids? By definition, there are no galaxies in the volume-limited surveys. They have 0 density, but in that sense, but you can ask, what about the fainter galaxies? And here's just a little bit more detail. The top is a histogram of the density of the fainter galaxies in a void. In other words, you find the voids that are completely empty based on the volume-limited sample. Then you ask how many of the fainter galaxies that were rejected from the volume-limited sample. Oh, 2 minutes. Okay, sorry. And so what you get this distribution, and this is normalized to the total mean density of these fainter galaxies. And there's a spike. There are 2 histograms, one done with Bayesian blocks that's without arbitrary binning, and then a regular histogram with actual binning. And in both cases, there's a big spike of truly empty voids that have no galaxies from the faint end of the survey either. And so the distribution hovers around 10% or less of the average density. And again, a lot of the faint galaxies that are in the void technically are near the edge. This is a histogram of the distance from the edge normalized to the size of the void, and you see a good number of the galaxies are sort of not really in the void because they're close to the edge. So anyway, that's the kind of the summary of the statistical results, and the rest is just some philosophy. This is a philosophical slide about the relationship between the Voronoi representation and density versus emptiness, and trying to get at these concepts. I just threw in dark matter and dark energy because every talk has to have some reference to dark energy and dark matter. I have no idea if that makes sense at all. And finally, here's another sort of hinting at this duality. Are the voids distributed in the same way as the galaxy, as the clusters? Are there sheets and filaments and so on? One of these symbols represents the Voronoi cells, and the other represents the Delaunay cells, and I'm not going to tell you which one is which. These are three different projections, and that's the 3D plot. And I can't really tell any systematic difference between them. And finally, this notion is pretty old. I think this may be the wrong reference, or there's a more recent paper, but this interesting topological study by Gade et al. Shows a similar thing, where the low density regions and the high density regions kind of have a similar distribution. And here are my discussion questions. I know I'm near the end, but I just want to make the point that a lot of other void finding techniques find local minima in the density. This technique finds truly empty voids, or at least to the limit of the survey. And I didn't show it, but there's very little correlation between what we find in this study and the so-called catalogs of low-density voids. So are we finding something totally different that's unrelated to what people have called voids, or are they really similar? There's a lot of talk about a hierarchy of voids, which I find no evidence for. I think that's again, I'd like to discuss that, and then the obvious other things are here. Thank you very much.
I think I'm just going to exhibit my ignorance, but could you say a little bit about what the distribution of densities is in the Millennium simulation rather than in the Sloan data? In particular, something like a cumulative distribution that showed the fraction of the universe that had a density less than some fraction of the critical density, for example.
Those are pretty similar. In everything we did, there's no statistically significant difference between statistical distributions for the actual data and for the Millennium simulation. Others here may have worked with other more recent simulations, may want to answer that question in a different way, but I think there's very good agreement between reality and the simulations.
Well, what fraction of the volume of the universe is at a density, say, less than a third of the average density? Something like that.
Well, let's see. I think I can answer that. The voids that I found, which are roughly 10% or less, is a total volume of, I think, 3 or 4% of the volume of the universe.
3 or 4% of less than 10% of the average.
Right.
Yeah.